Hello everybody, I hope you're doing well. Welcome back to another video in our Introduction to Calculus playlist. So, in the previous video, we have gone over an intuitive way to understand rate of change of a function at a given point. So, just to jog our memory, right, we have this function here that I'm about to draw called f, and the curve of f might go something like that, right? So let's say this is y equals f of x. And we have this blue point right here called C, and the value of this is f of C. We wanted to figure out how can we get the instantaneous rate of change of a function f at the point C. And we discovered in the last video that we could just take a second point shown in orange right here and move the second point closer and closer and closer to this blue point so that when we're taking the slope between a line going through the blue and the orange point, the line is going to mirror more of the instantaneous rate of change of f at this blue point. And the line is going to become more and more tangent as shown in yellow. So right now the line would look something like this, but then if we moved the orange point more like here and we redraw this line in yellow, the line is going to look more something like that. And you see this line is going to become more and more tangent to this blue point, and it will look more something like that. And we formulated this discovery through the limit definition of this instantaneous rate of change. And if we recall in the previous video, if we evaluated this limit right here, or the equivalent formulation, we're able to use these limits to get an approximation for this instantaneous rate of change, or in other words, the slope of this tangent line right here, as we move the orange point closer and closer to the blue point. So today in this video, we're going to see these tools in action with an actual function. And hopefully through this exercise, you will actually understand where this instantaneous rate of change really manifests itself. So the problem we're going to be focusing on for this video is, let's say we have a function f of x equal to x squared, and at x equals 1, find the instantaneous rate of change at x equals 1. So we want to find the instantaneous rate of change of f at x equals 1. And recall in the previous video, we've dubbed this instantaneous rate of change, this word, aka the derivative. So we essentially want to find the derivative of f at x equals 1. And we want to use our tool that we've developed right here, these limits, to solve that problem. So the way I'm going to approach this is I'm going to first draw a graph of f so that we have a visual to go off of. So if you recall, right, the graph of y equals x squared is going to be a nice parabola. So we have this axis here, then we have x equals 1, 2, 3. Then we have like 1, 2, 3, 4. So we have 1, 1, right, for f of x equals x squared. And then we have f of 0, and then f of 2. Then we have negative 1, negative 2, negative 3. And I'm going to trace this in yellow. So this is f of x right here, right? So we know f of x equals x squared at x equals 1, f of 1 equals 1. So the blue point of interest is this point right here. And what we're going to do is we're going to use a discovery we've talked about in the previous video, where if we want to find the rate of change at this blue point, we need to find a second point that is close to this blue point and move the second point closer and closer and closer to this blue point in order to get this tangent line and, find the instantaneous rate of change. So let's do that. And so let's do that. So I'm gonna pick a couple of points that are close to this blue point right here. So for example, a starting point that we could use as our second point could be this point right here. This is 2 comma 4, right? Because f of 2 equals 4 in the function f of x equals x squared. And what we would do is we would take the slope of the line going through these 2 points, and then we're going to move this yellow point closer and closer. So let's say we did f of 2 as our second point, then we can kind of move the x value of this yellow point maybe to say 1.5, right? So I might move this yellow point down here. So 1.5 is here. And then we again, take the slope of the line, going through this new yellow point and this blue point. And then we can move this yellow point, again, very, very close to this blue point. So let's say it's right here. And then if we were to draw the line going between this blue and this yellow point, the line is going to look more like that. And we see this blue line is kind of intersecting this, curve of y equals x squared, right? Just at this point of x equals 1. So it's kind of just, skimming the y equals x squared function, but just at this point. So we know we're getting closer and closer to this supposed instantaneous rate of change, right? Now, how are we going to see this in action? I can show you a picture, right? But a picture is not as interesting. Let's actually see some numbers in action. So what I'm going to do is I'm going to make a table, right? So we have, the various x values, right, for our second point. And then we're going to have a value for, the slope. And just to tie in the limit definition we found from the previous video, for convenience, I'm going to use this limit definition right here. You can definitely use this limit definition here, but recall what h is. H is kind of the distance between the x value of, this blue point of interest and the second point, right, that you're using to take the, slope of the line that goes through the 2 points. So you can use this first limit definition here, like just to walk through the table with me, or you can use this definition and kind of follow me. So we have this second point x, right? And then the slope slash rate of change. And I'm going to write the limit definition right here for reference that we're using. So we're using this limit definition here. So the limit as x approaches c of f of x minus f of c over x minus c. And in this case, since we're trying to take, since the blue point is at x equals 1, and our second point that we're using as reference for this rate of change is going to approach 1, in this case, c is going to be 1. So in our case, right, this expression, right, this limit statement for our purposes boils down to the following. So the limit as x approaches 1 of f of x minus f of 1 over x minus 1. And we know f of 1 is going to be 1. So this gives us a handy way to kind of get the slope as we move the second point closer and closer. And for convenience, I'm going to take the second point to be kind of points that are to the right of this blue point. And we'll come back to, the fact that we could potentially use points to the left of this blue point and conduct the same experiment. But for convenience, I'm going to use, points to the right of this blue point in order to, find this instantaneous rate of change. So let's roll with it. So let's say the first point is at x equals 4. So this will be f of 4 minus f of 1 over 4 minus 1, right? Because this is going to be the slope, right? And this is going to equal 5 if we use our calculator and plug the numbers in. So we see that, if we used 1, 1, comma 4, comma 16, right? as the 2 points, then the slope of that line, right, consisting of those 2 points is going to be 5. But maybe 4 might not be close enough in order to get a good idea of this instantaneous rate of change. We got to like move the second point much closer, right, to x equals 1. So the next value we can try is x equals 3 as our second point. So this would be 3 squared minus 1 squared over 3 minus 1. Remember what the original function is. F of x equals x squared. So this will be 4. And then we're going to keep adding more x values, and we're going to find the value of these slopes. So here we have x equals 2. And the value of the slope is going to be 3. Then we're going to have 1.5. And then we're going to have 2.5 as the value of the slope. So this is equal to 2 squared minus 1 squared over 2 minus 1. This is going to be equal to 1.5 squared minus 1 squared over 1.5 minus 1. Okay, so 1.5 is getting close to 1. So let's get even closer and see what this instantaneous rate of change is approaching. So we have 1.1. This is cutting it pretty close. And the value of the instantaneous slope, the value of the slope here is 2.1. So what does that correspond to? It corresponds to this yellow point kind of moving really, really close, right? And then, we're taking the slope of the line that goes through this blue point and this increasingly closer moving yellow point. So we have, the slope using 1.1, x equals 1.1 as the second point is 2.1. Okay, we're getting even closer. Let's try 1.0001. And the value of the slope using this x equals 1.001 as a second point is 2.0001. Okay, seems like the slope is approaching a value. Let's do one more really, really close second point. So let's say we use 1.0000001, and the value here is going to be 2.0000001. Okay, we're getting, looks like, here we're clearly approaching like 2, but the slope is like just a little above 2, right? So maybe, the slope, the instantaneous slope seems to be approaching 2. And if you want to see, like, if you want to confirm the suspicion, we can try plugging a really, really, really close number to 1, right, as our second point. So imagine adding a bunch of zeros and, doing something like 1.000000001, and you kind of get, what's the slope here, right, using the approaches we've been doing with the past values in this table. But we see maybe this instantaneous slope is approaching 2 because maybe this point is like really, really close already as our second point to the blue point shown here at x equals 1. But before we kind of confirm our suspicion, I think, it's good to kind of maybe consider second points that are like kind of just to the left of this blue point, but like they get really, really close, right? So similar effect here, but like except using points here as our second point. So let's draw that. So maybe we might have, a second point right here, and the line would probably look something like that. Let's say we move the second point somewhere to here, then, the line going through would be looking something like that. Maybe if we do, once again, we move this second point right next to this blue point, but it's to the left, right? And if we draw this line, right, we see in yellow, right, it's kind of, becoming more and more tangent-like, right? So now for finding the instantaneous rate of change using second points, like, along with this blue point that are kind of to the left, we can repeat a similar exercise to what we did earlier. So if we look at our table here, notice that the x values we were choosing for our second points were numbers to the right of x equals 1. We could try repeating this exercise, but, you know, using x values that are kind of to the left of x equals 1. So let's do that. So we'll make a similar table right over here. And, you know, this part of the exercise is kind of the same thing as, what we did earlier. So I'm going to kind of speed through this. But so we'll take second point x values of 0, 0 0.5, 0 0.75, 0 0.9, 0 0.99, and 0 0.999. So at x equals 0, the slope we have would be 1, right? Because 0 squared minus 1 squared, all divided by 0 minus 1 is going to be 1. At x equals 0 0.5, the slope comes out to be 1.5. With x equals 0 0.75 as our second point, the slope comes out to be 1.75. With x equals 0.9, the slope comes out to be 1.9. X equals 0 0.99. 0 0.9 is cutting close to that x equals 1, which is what we care about for finding the instantaneous rate of change as part of this exercise. So this would be 1.99. And at 0 0.999, cutting it really close here, we're going to see that the slope turns out to be 1.999. And we see here the slope seems to be approaching 2 as well. So it looks like if we use, x values to the left of this x equals 1 to motivate our second point in order to kind of take slopes of, these lines, um, we're seeing that the value of the slope is kind of approaching 1.999 from using x values to the left, and using x values to the right, we're seeing a similar behavior. So it seems safe to say, right, that we've kind of checked our cases, and through this, we can say that the instantaneous rate of change of f of x equals x squared at x equals 1 is 2. So we can say that it's fair to say that the instantaneous rate of change, or the derivative of f of x equals x squared at x equals 1, is 2. And that concludes this video. And now that we're able to go through this exercise, you might be wondering, so do we have to do this for every single function, for every single x value? And the answer is you don't, because we will introduce some tricks that can help getting the derivative of functions at certain values of x very, very easy. But I think it's important to kind of go through this exercise like at least once or twice so that you can kind of get a feel and an intuition for what does instantaneous rate of change really mean, and how can we see this in action with, the tools that we know from, the limit chapter. So that's a wrap for this video. And as usual, don't forget to like and subscribe. And I will see you in the next video where we will start to, wrap up this idea of instantaneous rate of change and kind of proceed to finding or coming up with rules that can help us calculate these derivatives much faster in a much easier way. So see you in the next video.